Hey guys, welcome to this video series on chemistry. So in this series we are going to start exploring the basics of chemistry. We're going to look at what the atom is. We're going to introduce you guys to the periodic table and trends in the periodic table, how to read it and how to understand it. And then we're going to go into two particular types of chemical bonding, which is ionic bonding and covalent bonding. Okay. In this video, we're going to focus first on the atom. We're going to introduce you to what the atom is and the structure of the atom. So let's jump straight into it. Okay. So the atom. We're going to start by looking at the structure. Now, the atom comes from the Greek word atomos, which means indivisible or undivided in Greek, and it was proposed by a philosopher named Democritus, who thought that at the time you cannot possibly get anything more fundamental and basic than the atom, that everything in the world and the universe was made up of the atomos particles. Okay, we know that not to be true, but by definition the atom is the basic unit of matter. For something to be considered matter, that is physical and takes up space, it must be made up of atoms. Okay. So all matter is composed of atoms, previously thought to be indivisible and small. However, we know that's not true. We do know that the atom contains three particles. Okay, you've got the protons, which have a positive charge, and they are particularly large, like the one shown in the diagram here. We have the neutrons, which are of no charge, the ones in yellow there. And then we have the electrons, which are the small stuff orbiting around the outside, which have a negative charge. Okay. Now, the nucleus, which is the center of the atom, is composed up of protons and neutrons put together, and the electrons kind of orbit around the outside. Now, even though this is kind of the fundamental basics of atomic structure, we actually know now through a new area in science called quantum physics and things like that, that this isn't the actual structure of the atom. Okay, so what I'm going to be teaching you guys on how to understand is only really relevant for the first section of the periodic table of elements, and it is somewhat of an outdated model for the atom. Okay, so the actual structure of the atom looks a bit more like this. The electrons don't actually orbit in these neat layers called shells. Instead, they actually form an appearance within regions called clouds, and they have a set probability of appearance. Yeah. So if I was to represent it using a diagram, you would have your nucleus in the middle, which is your protons and neutrons, and then you have the electron cloud forming around, and they have an increased probability depending on what the position is. And we can look at that and predict based on sort of which regions form which clouds. Now, you may have seen this occasionally when you look at different structures of electrons within the atom, and you hear these things called p shells and s shells and all those kind of things. That's what they're referring to, the cloud regions. Okay. Now, we don't teach this in a year 10 level. In fact, it only gets picked up in VC chemistry. So from about year 7 to year 10, this isn't taught, mainly because it's quite a complex model and at a university level, and to truly understand it takes a lot of time and effort, and it's a little bit complicated for you guys at the moment. Alright, so let's take a look at the structure. Now, it's very useful when we're going through this video series to actually have a periodic table in front of you, because I will be referring to the periodic table back and forth as we go. And every time I bring up an element, you kind of need to have the periodic table in front of you to refer to the element and understand what I am talking about. Okay, so let's take a look at hydrogen. This is what hydrogen will look like. Hydrogen is one proton in the nucleus and one orbiting electron in the shell. Okay. It contains one proton, no neutrons, and one electron. Okay, that is what hydrogen is made up of. One proton and one electron, and it looks like this on your periodic table. Yeah. Now, the numbers can change in terms of where they are positioned, but at the end of the day, there are a few key things in the periodic table that you should always recognize. The first is the big symbol. Yeah, this hydrogen is represented by the letter H in capital, and that is what we call the chemical symbol or the chemical formula. Okay. With regards to the chemical formula, the first letter is always a capital, and all other letters are lowercase. So, for example, if you jump to helium, you will notice that helium has a capital H, but a lowercase e. Now that is always the case to indicate that every time you see capital H, lowercase e, it is helium, okay? And then there's a few other things you need to know as well. This little number in the top corner, sometimes it's in the top left, sometimes it's in the top right. Either way, it's what we call the atomic number. Now the atomic number helps us identify how many protons and how many electrons the atom has. So in the case of hydrogen, right, it has an atomic number of 1 because it has 1 proton and it has 1 electron. It is not, 1 is not the collective amount. 1 represents both protons and electrons, okay? The larger number down the bottom is what we call the relative atomic mass. Now, the relative atomic mass tells us the combined mass of the protons, the neutrons, and the electrons. Now, you will notice that hydrogen has 1.0008, okay? At first glance, you might think that that is representing the total mass of protons and electrons, and that is kind of true. It is representing that, but it is what we call a relative number, and is relative to carbon-12. And the reason for that is because when scientists were first trying to calculate relative atomic mass, they figured out that about one gram or something of carbon has an exact amount of atoms in it, which you can actually calculate, representing by a capital letter N. And so they use that as a bit of a benchmark to weigh up where all the other atoms will be. And the reason for that is because you can't weigh atoms. Atoms don't have a weight, because in order for you to have a weight, you have to know what the object is made up of, yeah, in terms of its atoms and its elements. So for atoms, they don't have that same kind of measurement capabilities, and so that's why we use a relative number to carbon-12, carbon-12 being the benchmark element, okay? Okay, let's look at helium. So this is what helium looks like in terms of its diagram. Hopefully by now you can figure out the plus there are the protons, and it has 2, 1, 2. The N is the green one is the neutron, which have no charge, and helium has 2, and there are 2 electrons. Okay, so if you would look at your periodic table, you will notice that helium should have an atomic number of 2 because there are 2 protons and 2 electrons. And you could then kind of estimate what you would expect its relative atomic mass to be, which should be somewhere around 4. 2 for the protons, 2 for the neutrons. Because the electrons are so small, they are somewhat negatable. You can kind of ignore it in terms of its actual mass, okay? And you can see there, so 2 and 4 being the atomic number and the atomic mass there, okay? So a few key aspects, okay? So we talked about looking at that. So relative atomic mass is mainly from protons and neutrons. So using the atomic mass, you can actually back calculate the number of neutrons by minusing from the atomic number, okay? And the reason for that is because electrons have very little mass, and so we ignore it. And then we can figure out the number of neutrons by minusing the atomic mass, rounded off by the atomic number, okay? And so the atom's different from one another purely by the number of protons and electrons they possess, okay? What makes hydrogen different from helium is the fact that hydrogen has 1 proton and 1 electron. Helium has 2 protons, 2 electrons. And so if we go to lithium, you would expect that lithium, which is the 3rd element in the periodic table, would have 3 protons, 3 electrons, as opposed to 2, okay? And that's what you see there. So lithium actually has 3 protons and 3 electrons, okay? And it has 3 or 4 neutrons in the inside of the nucleus, okay? The relative atomic mass for lithium is 6.941. Now you may notice something a little bit odd about lithium that you didn't see in helium and hydrogen, and that is this idea here, right? This idea that the number of neutrons in lithium can be 3 or 4. There is actually a difference there, okay? And that brings us to the idea that not every atom is the same as every other atom, okay? Think of an element as being like a species of the same atom, right? individuals within that species can differ slightly. And in this particular case, you actually have two main different types of lithium, okay? And those variations are actually what we call isotopes. Isotopes are variations of the same species of atoms, the same atom, because they'll have the same number of protons and electrons, but they have a differing number of neutrons, okay? So in this particular case, lithium has two isotopes. Lithium-6, which would have 3 protons and 3 neutrons, yeah, which is this one here, and lithium-7, which has 3 protons and 4 neutrons, okay? And so that gives us an indication of the different types of lithium out there. And in fact, it is because of this difference here that we don't get an exact 6.941. We don't get an exact 6 or an exact 7 in terms of its atomic mass. That's why it's relative. What that means is this number gives us an indication of which one is more commonly occurring in nature, right? Because 6.9 is closer to 7 than it is to 6, you would expect that the majority of lithium would actually be lithium-7 with 3 protons and 4 neutrons, as opposed to lithium-6, 3 protons and 3 neutrons, which is why the average there is 6.941, okay? Now this isn't always necessarily true, because some atoms will actually have 3 different isotopes as opposed to 2. Yeah, so for example, iron actually has 3 different isotopes containing different numbers of neutrons, and so that calculation doesn't always come out as smoothly as you would expect. Okay, all right, we're going to take a bit of a twist and start looking at electron shells. If you look for sodium in your periodic table, you will notice that sodium looks a little bit like this. Okay, the periodic table is extremely useful to give us a very key understanding of the structure of atoms, in particular the electrons, because it is the electrons that we are really interested in, the way they interact and how they form their chemical reactions that you observe in pretty much all of the chemistry that we do. Okay, if I was to show you a diagram of what the electrons look like when they orbit around the nucleus, this is what you would see. Now, keep in mind that once again, as I put the disclaimer at the start of the video, that this is an outdated model. Okay, it's an old model and it's an old interpretation of the atomic structure and the electrons. It is useful to learn and to figure out the patterns, but it is not, in today's age, a current representative of what atoms and the electrons actually look like. Okay, so sodium, the nucleus in the middle. For the purpose of this diagram, I've ignored the protons and the neutrons, and we know that they sit there. You would expect that because it has an atomic number of 12, it would have 12 protons, and because it has a relative atomic mass of 22.9, if you round it off, you get to 23. It would have 23 minus 11, which would give us 12 neutrons. Okay, so sodium would expect in the nucleus to have 11 protons and 12 neutrons. Okay, it will also have 11 electrons, and that's what we're going to try and draw. It actually has 2 in the first shell, it will have 8 in the second shell, and then it has 1 in the third shell. 2, 8, 1. This little diagram here is the electron shell structure, okay? And the reason why it is like that is because atoms in nature follow a particular pattern in order to become energetically stable, yeah? The electron sitting in this orbit contains energy, right? And when they reach a certain number of electrons, they become stable. So atoms are stable when that shell that they occupy, when it becomes filled, they will become stable, and then they will shift to the outer shell. They start with the first shell, and then they slowly expand and get larger and larger, as we see. Now the first shell is stable with 2 electrons. The rest of the shells number 2 all the way to the 7th shell, which is the maximum number of shells of all the elements at the moment, is stable with 8 electrons. Yeah. So using that pattern, we can figure out how many electrons would usually occupy these shells before they move on to the next shell. Yeah, it's 2, 8, 8, 8, and so forth, okay? This is what we call the octet rule, which means atoms achieve stability energetically by having 8 electrons in their shell, right? With the exception of the first shell, which only wants 2, okay? And the electron that are doing that filling up process are what we call the valence electrons. They're the ones that are occupying the outer shell, right? And so you can sort of see here, sodium will have in its first shell 2, and that's stable, so it moves on to 8, and then it fills up the 8, and then it'll move on to the next one, which will have 1. Now, if you take the next element after sodium, magnesium, with an atomic number of 12, you would expect a very similar pattern where it would have 2 in the first shell, 8 in the second shell, and then 2 in the third shell, right? And then you can sort of keep going and get to aluminium, which has an atomic number of 13, and it will be 2, 8, and 3 in its outer shell, and so forth, and so forth, okay? Every time it gets to 8, the shell is full, and it moves to the next shell. Okay, that little number there is called the electron configuration, yeah? And it's a set of numbers that gives you an indication of which shell and how many electron is in which shell. So 2, 8, 1 being the electron configuration for sodium, okay? So using this understanding of the electron shells, we can actually figure out the structure of the first 20 elements. Based on the octet rule, the rule of 2, 8, 8, 8, we can figure out exactly what they would look like just based on their atomic number. So now, by this stage, if you have time to actually sit down and actually start drawing out the configuration of the first 20 elements, sodium at 11, for example, if you went down to oxygen, which has an atomic number of 8, then see if you can try and draw what the electron shell configuration would look like, okay? The biggest disclaimer here is that this particular model, because it is outdated, will only work for the first 20 elements. In other words, you will get from hydrogen down to calcium, and you won't be able to get further than calcium, because when you start shifting into the transition metals, which is the yellow block in the middle of your periodic table, when you get into that, it actually becomes more complicated, and they follow a slightly different rule, a more updated rule, which we are not going to go into for the purpose of this series. Yeah, so just be aware that this model that I am teaching you guys here is only relevant for the first 20 elements. Once you go beyond that, it doesn't work. All right, so carbon, atomic number of 6, therefore it has 6 electrons. That's what we're interested in, the 6 electrons, and the configuration will be 2 and 4. If you have potassium with 19, it has an atomic number of 19, it has 19 electrons, and it will have a configuration of 2, 8, 8, 1. Okay, do not forget to fill up the 2 in the first shell when you are determining your shells, otherwise you get a number that's completely warped. All right, so that's electron shell configuration, and that helps you guys sort of understand a little bit about the structure of the atoms, because later on when we look at chemical bonding, we use this structure to determine how atoms will trade electrons with one another. All right, so that's it for this week. Next week we're going to look at the periodic table, and we'll have a look. Sorry, not next week. Next video, we're going to take a look at the periodic table. How do we read the periodic table? What are the trends based on the atomic structure? And that'll help prep you guys for learning how chemical bonding works in elements. Okay, so I'll catch you guys then. See ya.